The next few examples we're going to do are really basic and important fundamental Fourier transform pairs. So it's important to know more than just the example. It's important to write down this Fourier transform pair someplace, just like you worked out some basic Laplace transform pairs at the beginning of the semester. Here's our first example. We'll start off with a function, perhaps it's a voltage, perhaps it's a current, and it's a impulse. And the question is find the Fourier transform. So if we were to graph it, it would be an impulse. It would have area 1, not height of 1. It has an infinite height, and it occurs at time equals 3. So here's our function. I suppose for completeness sake I should show it 0 elsewhere. And let's find its Fourier transform. First, recall what this impulse is. What's f of 1, for example? Well, to find that out, go across to where 1 is. You can see it's 0, so f of 1 is 0. What's f of negative 3? Same thing, negative 3. You can see it's 0. In fact, f of every number is 0, except f of 3, where it's infinite. So it doesn't really help us to talk about what f of 3 is. What we can talk about, though, is what it does under an integral sign. And if we were to integrate it from negative infinity over to negative 3, it would be 0, since there's no area underneath here. And in fact, if we increase the upper limit from negative 3 to 2, it would still be 0. But the moment we make that upper limit 3 plus or greater, 3.1, it all of a sudden changes to 1, since the area underneath that impulse is 1. All right, so this was just an aside to recall how impulses work. And let's get on to the meat of the question. The definition of a Laplace transform is its integral over all time of the function times e to the minus j omega t dt. No longer omega naught, since there is no fundamental frequency. So filling in what this value is, that gives us this integral at t minus 3 e to the minus j omega t dt. Now, what I've humorously called Squire's law says that whenever you've got these impulses or step functions under an integral sign, the first thing is to get rid of them by modifying your integral limits. Let's graph this, and then let's graph this, and see how we can use that to get rid of our integral limits. If we graph the first part in green, we have this. If we graph the second part in blue, oh boy, that's going to be complicated to graph because this is a complex exponential, so it'll have a real part. That real part by Euler's law will look like a cosine. It'll have an imaginary part, which by Euler's law will look like a sine. And how do I graph a real and an imaginary part? I don't know. So I'm just going to squiggle it and give up. But now I can multiply these guys across, and when I do, I can see that no matter what this is doing, this impulse is 0 everywhere except for t equals 3. So when I multiply them together, I've got to get something that's 0 everywhere except at 3. And when it's 3, it's going to be the height of the impulse times whatever this thing is doing at 3. What is this thing doing at 3? At exactly 3, this is not e to the minus j omega t, but at exactly 3, the height of this is e to the minus j omega 3. Since at t equals 3, we replace 3 in t and we get e to the minus j omega 3. So at 3, we multiply this number by this number, just like up here we're multiplying green by blue, we multiply green by blue, and we get a impulse. And instead of having area 1 now, it has to have area e to the minus j omega 3. Now the integration is really easy. In this recall box, we said that the integral of an impulse is just the area of the impulse. So this integral has to be equal to just e to the minus j omega 3. And that is, in fact, the answer to this question. This is what f of omega is. But more importantly, we found our first pair. And so our first pair is, in general, if f of t has a transform of f of omega, so this is our time domain world, this is our frequency, our Fourier domain world, then any impulse that's been delayed by t naught will have a transform of e to the minus j omega t naught. We're going to build this table because it's really hard to work these things out every time. And I'm going to give you another transform pair that we're not going to take the time to derive, but just trust me that this works in the opposite way too. If you have a e to the j omega naught t in the time domain world, so this is some sort of complex exponential, that corresponds to an impulse that's been delayed in the frequency world. And just to make it a little challenging, we've got a 2 pi in there too. But the idea is that impulse in one domain goes to a complex exponential in the other domain. Complex exponential, impulse. If you're wondering why the 2 pi got in there, there's different ways to define what the Fourier transform is. Mathematicians define it with a 1 over square root of 2 pi in there, which makes this thing look much more symmetric. Electrical engineers use a different formulation of what the Fourier transform is. I give it right here. And this is easier to work with, but you lose some of that beautiful symmetry. So this is the start of our Fourier transform table. Let's continue it on with our next example. And by the way, there is absolutely no intuition with this problem. It's all math.